And we have Christian. Could you introduce yourself, please?
Yes, also welcome everybody. I'm very happy that we can make this and having very good speakers today. My name is Christian Herglotz. Maybe you know me. I think everyone knows me by now. So I'm a project, well, I would say senior scientist. I've got a small group of researchers working on sustainable video communications with a big focus on video compression. And yes, I'm very happy that we are here now for this occasion.
Okay, thanks a lot, Christian. When we prepare and when we submitted this workshop, we had four main objectives for the workshop. The first one was to raise again industrial and public awareness for ICT and the sustainability of ICT. It's always important to remind us what are the problems we are going to face. The second objective was to monitor and to evaluate the energy consumption all along the video chain. The third one was to try to introduce new technology that would help us in order to reduce and to be more efficient in terms of energy consumption. Where are my screen? Okay. And the last one is just to present some new standardization activities that would help us to go further in to promote the different activities. So we have selected several papers, several speakers in order to cover the different objectives, and we will have today seven talks. So here is the program. So this is a short introduction on the top. So then we will have two presentations, one by Daniel Sheen, which is well known in the field, and Samira Asfal regarding the second objective, which is to monitor and to assess the energy consumption all along the video chain. And already we thanks a lot Samira, because Samira is at Vancouver and it's almost midnight. So this is very kind of her to be here. Then after the coffee break, we will have two other presentations, more about new technology in order to reduce the energy consumption of the video chain. We will organize, if we have enough time to do that, a very short panel, an open discussion in order to connect all participants and to tackle several points. We will see how we are going to manage these things. And then after the lunch break, we have three presentations. The first two presentations are dealing with new technology in order to reduce energy consumption. And the last one would be about the standardization, ongoing standardization activities in the context of ICT, the sustainability of ICT. Okay, Christian, would you like to add something? Or?
No, I think that's all for the introduction.
Okay.
We should try to stay in time.
Yeah.
We're having the first presentation in 2 minutes.
So Daniel, if you want to come.
Prepare.
Oops.
Thank you very much, Olivier and Christian, for inviting me. It's a big honor. This should work. Et voilà, ça marche. Good morning, everyone. Really nice to see you all again after the banquet last night. I tried to start with an attempt to contextualize, I think, most of the program today in the picture of climate change, the pressure and the urgency that we face to act. I will not repeat what Ranjoul, is that what that should I say, presented in his keynote on the science behind climate change. I will instead dive right into the projected pathways or the developed pathways that the International Panel for Climate Change has developed as an opportunity to cast forward a path that policy, industry, and society in general can take to get us to a significant reduction of carbon emissions, and to have a realistic chance to limit global warming to about 1.5 degrees until the end of the century. And they do this, this is of course looking forward and faces a lot of uncertainty, but the technique that is being employed is to develop different scenarios that describe alternative in broad brushes, different assumptions about the change of the economy and society. And even though they all have got some plausibility to themselves, there's one that stands out as being particularly appealing, and that's the LED pathway, the low energy demand pathway, because it does represent a set of changes, transformation to society that is assumed to be the least controversial and the most compatible with the current paradigm of economic growth, and tries to have a realistic chance to get us there. So part of all of these pathways is a decarbonization approach through electrification of much of the energy demand, and so besides this global perspective, we have similar pathways then broken down to the sectorial parts of the economy for individual countries. And what we have here is the 6 carbon budget in the UK. And you can see that they present 4 different sectors more or less robust projections of how they might get to a net zero world by 2050. Now, what we see here is that the ICT sector doesn't feature. The ICT sector there are certain projections, and I come to, well, there are certain models that describe the overall footprint of the ICT sector on its own, and I'll come to those in the next slide. But the ICT sector is, of course, part of the transition towards more efficiency that is behind those pathways that we see here applied to these other pathways. And so in the policy context, there's now a tension between the energy consumption of the ICT sector and its potential to result in decarbonization in other parts of the economy. Okay, so we need to keep that in mind when we're thinking about decarbonizing the ICT sector. Okay, so what we have here, this tree diagram, is a representation of global carbon emissions. There are a variety of different estimates. This one is from Climate Watch, I think. So there are others, but broadly the numbers are uncontested. And this tree diagram here includes agriculture as an important, significant part of greenhouse gas emissions. And what we have in the corner, the orange and the red box, is the portion of global carbon emissions that is at the moment assumed to come from the ICT sector. This is including the entertainment and media sector, actually, I should add, because this is based on numbers from Malmedine using data from 2015. So there's a bit of a mix here, using carbon emission data from 2020 and combining that with an estimate of the ICT sector from 2015. The sad reality is that there are very few recent estimates of the ICT sector's carbon emissions. So there's a big demand for an update, and there's one in the making, and I'll refer to that in a second. But we certainly will welcome many more. But if we combine those two, we end up with an estimate of the carbon emissions for the ICT sector of around 2.3%. And yesterday we saw that, for example, Freitag et al. In Lancaster, they have carried out attempts to deal with truncation errors that sometimes occur due to the LCA methodology that's being applied to generate some of those assumptions, and that has an impact that potentially the carbon emissions from the ICT sector are higher. But around about that number is the current consensus. There's some uncertainty. Okay. But actually what we're seeing here is suggesting, firstly, a very small carbon footprint of the ICT sector, and secondly, it combines it with the part of the economy that I think is not useful. It makes it more complex to reason about those. In agriculture, we saw yesterday that from land use change to carbon emissions, there's methane and a lot of other gases that are relevant greenhouse gas emissions. And so what I've got here is an attempt to narrow down the role of the ICT sector within the carbon emissions, the global carbon emissions, by removing the agricultural sector, and then using IEA data, just relate that to the emissions from electricity generation and heat. And if the overall pot, the size of the overall pot gets smaller, then of course the relative share for the ICT sector increases. And at this granularity, I've broken down the ICT sector into individual elements. So we now see data centers and networks broken up. Yeah, so this isn't the data that describes the ICT sector here. It's not my making. This is from Malmedine. In addition, we need to put more attention to the embodied impact. You know, this is something that we've heard during this week several times. So what I've also done is distinguish the embodied impact that we have in the data from Malmedine between embodied emission impact that comes from the use of electricity, which we can decarbonize if we decarbonize the electricity, and residual carbon impact within the embodied emissions that is not from electricity but from other processes. Yeah, so for example, leakage of gases or land use change. And the data here becomes really fuzzy, but there are some numbers out there that is in the order of 60% of the embodied impact that comes from the use of electricity during manufacturing operations. So I've split that up in the numbers here. Okay, and then the next step that we can take is we can remove heat. So we saw here, if we include heat, then the relative share of the ICT sector is 3.2%. But if we take heat out and we just look at electricity use, then suddenly the ICT sector, with 2020 carbon emission data combined with 2015 electricity and data, suddenly is responsible for about 10% of global electricity use. Okay, and now I was able to remove the part of the embodied emissions that is not from electricity. That's why I broke this up and made this distinction previously. Okay, and the interesting bit is that suddenly a number of 10% makes it easier to relate the footprint of the ICT sector to other estimates that we find on a national level of the role of electricity consumption from ICT. Yeah, so in the context of the UK, there are studies that look at energy demand, electricity demand in society, and often you find similar numbers. Or recently there was a program on the BBC looking at the carbon footprint and environmental footprint of data centers in Ireland, and they said that in Ireland, data centers are now consuming about 14% of electricity. And when you first hear such significant numbers, that doesn't really square up with an idea that the carbon footprint of the ICT sector is in the order of 2% of the economy. But when we're looking at electricity, then actually those are really compatible. Okay, so this is the price that is there that we want to attack. We want to move to this low energy demand world, and we want to. So that means we need to address those 10%. And how do we get there? What we've also learned this week is that for many of the parts, in particular the shared infrastructure, so networks and data centers, the trend is far from a reduction. We saw for the cellular network in France that actually there's a 20% increase of electricity consumption per year, and we also saw that based on the data from ETNO, in the European context, energy consumption for networks in aggregate remains relatively stable. But that's not where we want to go. We want to reduce the energy consumption. So we need to reason about what we can do, and what I've also got here. So I promised that there is now an update from Malmedine on their 2015 on the previous assessment of the energy consumption and carbon emissions of the ICT sector. There is a preprint available of an update that is currently under review. I've included the numbers here, but it comes with the disclaimer that they haven't been ratified. So if you search for Doug London's Google Scholar profile, then you can find the link to the data in case you're interested. And I think there's good reason why this needs to still be reviewed, because if you look at the estimate of the electricity consumption in that data, you see that it assumes a reduction of the electricity demand for data centers between 2015 and 2020, which I think is highly unlikely. And actually, the method that they used to extrapolate this is not parsimonious. I think they went a little bit too far in their attempt to keep things simple. And here's some indication for why the notion that electricity consumption by data centers would be reducing. This is from GLL, a consultancy organization that are tracking data center developments, and we can see that projected capacity increases are indicating that the demand for electricity is just going up and not down. Okay, so that's a warning, because it is really at odds with where we want to go. What is a positive story is the success that we have in Europe and elsewhere in the world on decarbonization of electricity. So these are just two snippets from the Carbon Brief set of documents and reports very recently, and they do show that there's a good direction of travel being achieved on the decarbonization of electricity. And in the UK, we had a really quite successful growth of renewable in the electricity mix, and going forward, the pathway that is being projected for further decarbonization of electricity offers the outlook that by 2030, carbon emissions would drop by another 75% from where they are now. This is a projection, so we don't know if it happens, but if it does take place, then that will really help in reducing the carbon emissions from electricity consumption. And it's interesting to find out how is that going to change the balance in the overall ICT carbon footprint. So this is a very simple projection. This is no projection. It's just a thought exercise. If the rest of the world was able to decarbonize at the pace that the UK is projecting for itself, which is already uncertain, And we know this is definitely not possible for the whole planet. But if there was a 75% reduction, then it would mean that by 2030, the use phase electricity consumption carbon footprint for the ICT sector would reduce significantly to the levels that we see in the blue box here. So that would be a fantastic story. However, this assumes a continuation of the growth that we've seen of the dynamics of change between 2015 and 2020. I did not correct the assumptions that were inherent in the update from Mahmoudine that we've seen just before. That's why we're seeing by 2030 an assumed reduction of electricity consumption by data centers, which is very unlikely, as we've just seen. Okay, so don't take this out of context. I'm not saying this is anywhere where we're going, but it illustrates that aggressive decarbonization of the ICT sector, of the electricity consumption, will benefit the ICT sector heavily. But the flip side of this is that the relative share of the manufacturing impact, of the embodied impact, will become more and more important. So the next question that we need to ask is, what is the opportunity here? How quickly can we decarbonize, for example, the electricity that is being used for making equipment? And one of the places where an enormous amount of ICT equipment parts come from, integrated circuitry, is Taiwan. And Gauthier Roussel and Thibault have carried out a fantastic study that you can find with this link, looking at carbon emissions of the electricity grid mix in Taiwan. And what they're finding is that due to the geographical conditions in Taiwan, there's very little opportunity for them to replace their current fossil fuel-based electricity mix with renewable energy sources. Excuse me. So this is that's a real problem for the ICT sector, because Taiwan, TSMC, and many other organizations are supplying a dominant share of the chips that are being used in ICT devices. Okay, so that's a problem, and here we see that. What have I done here? So this is, of course, again, one of those highly speculative forecasts, and you can see always when you have numbers past the decimal point, then it means that you cannot trust these numbers at all. But what I've tried here is to estimate how does the carbon footprint of the ICT sector change, or how do the embodied emissions change if we assume a 20% reduction of carbon intensity by 2030 in Taiwan. Yeah, so we're saying, and this is an underestimate of the potential to decarbonize the embodied impact. But if we can only reduce carbon emissions of electricity used for making chips by 20%, as it looks plausible to be the case in Taiwan, then we're ending up with a carbon footprint of around 300 megaton of CO2e, and this compares to 30 megatons from electricity consumption in the use phase. So this is it's a really problematic balance that we need to address. Okay, so I've used up the majority of my time just for context setting. I think this is useful, because we do need to start linking the global perspective of carbon emissions and decarbonization of society with where we are as an industry and the dynamics of change that are likely taking place. But actually, the work, the majority of the work that we've done in Bristol over the last decade or so has been on understanding the opportunity and the and responsibility of individual services to aid in this decarbonization. And why we do this is an attempt to illustrate this here. So what we're seeing, what I've got here is a causal loop diagram that describes in really broad brushes the relationship between system parts, and here it is the infrastructure, the service providers, and the demand by users, and they are in a relationship, and you can start anywhere in this picture, but if we start with demand, the users are consuming services at a certain intensity, and network operators, they are observing this demand. They are also extrapolating how this demand is going to change in the future, and in anticipation of this, are providing capacity and increasing the capacity of the infrastructure. And the organizations providing the services, they are themselves expecting a growth of this capacity, and they are coming up with new services that use this capacity. We're increasing the resolution of our videos, and this is only possible because our networks are becoming faster and faster. But it's just one example of how infrastructure enables those higher quality services. And users, they find appeal in those higher quality services, consume more of them, and in turn forcing the infrastructure providers again to upgrade their capacity. And so we are thus in a reinforcing feedback loop here. Now, this is, of course, a stark simplification of what's going on in the economy, because there are also factors that are slowing down the dynamic of this. But nonetheless, it is important for us to recognize this logic that is inherent in the system. And now, if we want to brace the growth of electricity consumption and the associated embodied emissions that we've just identified, then we can intervene in this system part. And one of the ways that we can intervene is on the level of the services. Okay. And I mentioned video streaming a couple of times. The first step that you want to take is understand what is the footprint of video services. And I've got here snippets from a report that the Carbon Trust has carried out based on models in 2022 using industry data, and I believe this is the most robust estimate of the carbon footprint for video streaming that is out there at the moment. And what we see is that the user devices play an enormously important role, and network equipment in the home. Okay, so that's important for us to take into account. We see again, this is now from the same report, perspective on how the carbon intensity of the electricity affects those results, completely uncontested. And again, the choice of the user device having an enormous effect. So if we want to identify ways to reduce the carbon footprint of digital services for video and others, if we enable consumers to have an enjoyable experience with the least power-consuming device, then that is a thing worthwhile doing. So this is pretty obvious, but it's very stark, the difference in energy consumption and power draw between those different devices. Okay, great. Now, we need to go one step further. We have so this is from the presentation that Doug London had yesterday, where he described the historical change of electricity consumption. This is reported data from environmental reports from the European network operators. I think this historical data is pretty solid. But what we're seeing is that we need to really distinguish between the energy consumption in the cellular network and the fixed line network. And hence that's why I factored out, I've got those two charts here describing the role of video for the data traffic observed in mobile networks. And on the in the top left, I apologize for the small font there. This is from a recent exercise that Ofcom, the UK networks operator, have carried out, and we see that, of course, over the last over 3 years, consecutive years, traffic in mobile networks is growing. So this is nothing new. But once we observe this, and we remember that there is this logic of a reinforcing feedback loop driving the upgrade of the shared infrastructure, including the cellular network, then that gives an incentive to intervene on the level of services. And in 2019, we carried out an exercise trying to estimate what would be the potential to reduce carbon emissions, that's the ultimate goal, by swapping, by modifying, in this case, YouTube, for those users that only listen to the music. It was an observed phenomenon, anecdotally, that some users just listen to YouTube for the music, but they don't actually look at the screen, and that's a waste. So with some publicly available numbers we carried out, we looked at 3 scenarios and came up with these values. Now, there's a big caveat, because in those models we have in this assessment we have applied a model that is called an attributional model, and we've seen from Gael and his team that a really very clear illustration that the lacking energy proportionality of networking equipment, but the same is true for data center equipment and for user devices as well, really forbids making projections about a change of electricity consumption and hence carbon emissions from the reduction of data volumes. Okay, so this is, and I'm going into this into more detail now. I just wanted to explain what we're seeing here. On the left-hand side is data from BT describing how energy intensity varies between different access network technologies, and on the right-hand side, data historical data from Aslan et al. That shows the change of the carbon intensity metric over time. How am I doing with time? I think I need to wrap up. Yes, I will. Okay, so now that's so these are very popular. We see these intensity factors being applied in projections all the time, but it is truly problematic because the energy consumption of network equipment is marked by what we see here in yellow, a very high static power consumption that is completely independent of use. What we have here is the utilization on the x-axis and power consumption on the y-axis. And so even if the utilization is 0, the power consumption is significantly high. And then as the utilization increases, there's a very small, in the order of 10 to 20% for networking equipment, change of power consumption on top of this baseline power consumption. Okay, now I've been criticized for criticizing the European the GSMA for going out with a press release where they said, I know people were concerned that COVID and the additional, the change of the way that we consume data may have had an environmental impact, but we can proudly report that despite an increase of traffic by 50%, energy consumption in networks has not changed. Now, it does sound very appealing. However, actually, what they're saying is that they were wasting an enormous amount of energy consumption before, because if there's no change from this increase of data volume, it means that there's a potential, there's a part of the infrastructure that just runs there and is not providing a service. Now, the GSMA and the organizations operating those networks, they have a tough time if they wanted to reduce this energy consumption. I'm not making anyone personally responsible for it. We are locked in as a sector, and we need to do something about it. But at the moment, we're just stuck with the way that these networking devices and other infrastructure is working. But just to illustrate the problem, if we use a very simple model of energy intensity and apply it to projections, then we end up with wildly inaccurate forecasts of potential carbon reductions from interventions. Okay. So what we need to do instead is we need to have a more realistic representation of the dynamics of energy consumption of this infrastructure. And Jens Malmedin, for example, has presented a model that he calls the power model, or that has been referred to also by the Carbon Trust as a power model. And this distinguishes between the baseline power consumption and the elastic elements of energy, of power consumption. And with this, it's possible to estimate how varying the utilization of a piece of network equipment affects its energy consumption. And what we see is, unsurprisingly, it affects it very little. Now, I'm just going to skip over this. Now, because of that, or maybe I do go back. Because this is the case, that the energy consumption varies very little, we need to ask what is it that determines the energy consumption? And the energy consumption is determined by the peak demand that is being required of the infrastructure. So as the peak demand increases, operators are forced to swap out equipment with devices that have more capacity. And even though there are efficiency improvements over time, the increase of traffic demand does more than compensate and eat up those improvements. So what we would expect is that ultimately there's a growth of energy consumption as we see in the mobile network. Yeah. Now we don't see it in the fixed line network because there's a legacy equipment that is being switched off. Here on the left-hand side, the PSTN part of the network. But once that has happened and the entire network is modernized and IP-based, those savings, they'll be gone. And then we'll be, it's uncertain what that means for the core network as well, okay? Right. So just quickly, a question that I asked Gael after his presentation is, how do we now reason about the role of traffic outside of peak? So we want to reduce peak because we realize this is a pressure. This is a part of this causal loop diagram, a pressure on operators to upgrade their equipment. And if we can enable them to delay the increase of capacity by shifting our demands away from the peak, then we are working together. We are getting to a place of cooperation across the stack. Users can interact with this, and service designers, they can all work together to help keep energy consumption in check. So this is what I think needs to be explored by us collectively. The final thing I want to point out, I'm not going into detail, you can find a paper that is currently under submission to the International Conference of Image Processing. Image Processing, ICIP, yes? Okay. And this asks the question of what is the opportunity from reducing the bit rate for a large and significant video streaming service. So in this case, this is social video on demand, as is classified by Ofcom, representing, for example, the YouTube viewing in the UK. So it's about an hour a day. But if we assume all of this was HD, 1080p, and we reduce the resolution to 720p, what is the price? What do we get from it? And then we need to also take into account how the viewing behavior varies over the course of the day, because the electricity consumption changes, the electricity intensity changes over the course of the day. And we carried out this analysis, and it turns out, due to the inelasticity of many elements in the overall system, the reduction of carbon emissions is not statistically significant. It's in the order of 0.5 gram per user per day. And to just put that into perspective, a bowl of muesli, just a muesli, no milk, has 1 gram of carbon per gram of muesli. Yeah, so 100 gram of muesli, which is a reasonable portion, has 100 gram. And this change here has the potential to reduce carbon emissions by 0.5 gram. So not worth doing here. This is only the short-term perspective. What we need to also take into account are more long-term effects that then can enable a change of the infrastructure. I leave it here, slightly over time. I hope this is a stimulus for many of the discussions that we're having today. Thanks.
Thank you so much, Daniel. Thank you. Yes, we are running out of time, but anyway, I cannot stop Daniel. It was so interesting. So perhaps you can have one short question in the audience. Christian, go ahead.
Yes, so first of all, thanks a lot for all those numbers and those very nice speculations. Now I know that we know a lot that is very, very uncertain.
Yes.
But I think this is what we need to do, and we have to come up with ideas on that. So a quick question on that would be, you said that we have this big overhaul of static offset. Isn't there, from another perspective, a possibility to configure and construct servers and networks that would switch off and reduce this in case there is little traffic, which could also have a great impact? Can you comment on that, please?
Yes, it does sound very plausible, doesn't it? I think anecdotally, so without having operating these systems myself, that this is not current practice. There's a variety of factors coming in there, but I want to just highlight that the network operators themselves are constrained in the things they can do by the regulator. They are by law required to operate these networks with a high degree of resilience, and that limits their ability to operate their infrastructure in a leaner way. Yeah, so this is a tension. There's some engineering solution. There's a regulatory constraint and influence. It's a complex system, but absolutely in general, the practice, the way that we operate the infrastructure, and also how the community of engineers is designing this has a big potential to increase the elasticity. Yes.
Okay. Yes, thanks. And if I may, another maybe a little bit of mean question. So we've seen the rise of AI and huge of tons and a lot of demand by AI, which is increasing exponentially. So it's incredible.
Yes.
Right now, it's not really yet at that point where I would say, okay, it's in a similar order. But if we forward what's happened or we look into the future, shouldn't we right now start focusing on AI instead of ICT because it will be irrelevant in 10 years?
Well, I would say AI is part of ICT.
Mm-hmm.
Yeah. So that's the first thing.
Right.
Secondly, absolutely. I think where I said before, the data center projections of data center energy consumption growth, I think they're to a large degree fueled by the demand for artificial intelligence services. And then thirdly is a warning that the projection of future developments of electricity consumption or anything else based on assumptions are modeled on the current conditions is very problematic because that is inherent in the marginal behavior of the system. Yeah, the infrastructure scales as if we increase the amount of service that we get out from this. The efficiency changes, operators are going to change the way that these systems are run. And so just doing a projection of where are we now, imagine everyone is using this in exponentially greater amounts. We would consume more, what was we had an example here with the projection of base stations for the US, yeah, where the number was 600 million base stations in the US, and this is a kind of projection that takes a steady state assumption of the system and extrapolates based on some intensity, but that is highly problematic. Okay.
Thank you.
Thanks.
Okay, thanks a lot. We have to move on to the next speaker. So thanks a lot, Daniel. Okay. Hi, Samira. Thanks a lot for your patience. So Samira is in Vancouver, so almost 1 a.m. So thanks a lot for making this talk. So if you can share your screen, we see you on the very big screen here. We can hear you, but if you can share your screen, it would be perfect.
Okay, I will share that. And
Okay, perfect.
so you have my screen in
Yes.
present mode, yes?
Yes, so now you can start when you want.
Okay. Just a second.
Okay, go ahead.
Thank
please.
you so much.
Thanks.
Thank you so much for inviting me. And this is Samira from University of Klagenfurt. I really like to be there in person, but unfortunately I couldn't. During this presentation, I'm going to talk about the components that contribute in energy consumption in video streaming, the measurements, and the challenge that we have, and also the strategies that we can have for reducing the energy consumption in video streaming. So I will start with, before we begin, I would like to have a preview, and I will start with introducing our Athena team, Gaia project, and the motivation behind this project and research. Then I will delve into the carbon emission measurement. I will discuss about the components that contribute with energy consumption. Then I will introduce energy measurement tools. Then talking about the challenge and strategies, also talking some about our publications, and finally concluding with some remarks. Here you can see our team. Athena comes from adaptive streaming over HTTP and emerging network multimedia services. It's jointly proposed by the University of Klagenfurt and Bitmovin. The head of the team is Professor Timmerer. And in this team, we work on content provisioning, the delivery, and the consumption of the video, and from end-to-end perspective. So now we also started an exciting project dedicated to the energy consumption in all parts of the network, and it is called Gaia. Actually, with this growing concern for energy consumption and its environmental impact, it's very important that we consider energy consumption and CO2 emission for the video streaming. And there is urgent action needed against climate change and global greenhouse gas. And the carbon footprint internet data traffic accounts for about 3.7% of GHG. And actually, the significant part of this data traffic is video streaming. Gaia is intelligent climate-friendly video platform, and the word comes from the Greek goddess of earth or mother of all life. It's funded by FFG and a cooperative project between Bitmomin and Alpen Adrian University. And the leader of the projects are Christian Timmerer and Professor Radu Pradhan. So in this, we want to completely be aware of energy in energy consumption in different parts of the network, from encoding, delivery, and streaming, delivery and consumption. And another important thing that we consider is reducing energy consumption and reducing GHG emission. So I will go to the carbon emission measurement. The first important thing that we should consider is variability and uncertainty for carbon footprint measurements. Variability refers to varying from the country-specific emission factor, for example, end-user device technology advances and network energy intensity. Country-specific emission factor of electricity grid, that it can be, for example, Germany's grid emission factor is 30% more than 30 times more than, for example, Sweden's. So it's very so it means that the overall CO2 emission is 30 times more. And for example, regarding end user devices, if we have 50-inch TV, so we have 4.5 times higher than a laptop and 90 times higher than the smartphone, the consumption of the energy. And for example, regarding the technology advances, the technology advances actually over the time. So the time over the years, so the time that we are measuring the energy, it's really important. And regarding network energy intensity, because the country is important, the age of the network equipment is important, population density is important, even climatic factors like humidity and temperature. Another thing is uncertainty, which refers to the precision of the accuracy of the measurement. So for sure, it depends on the different allocation of the methods that we have, limited amount of data that we have available publicly, and the tools that we use for our measurement. That we need to consider for carbon emission is energy source. It means that the sources that we use to produce the power, that sources could be from the green or renewable, or could be from the brown or not renewable. With green, of course, something like solar, wind, but for brown, for example, it could be coal, it could be gas, nuclear. So the source that are using to produce the power is important. Then another important thing that should be considered is that some countries, they import, for example, electricity. And the electricity that is importing maybe is, I don't know, from a green or brown. So these are also should be considered. Another important thing is about the time. For example, if it is during the day, maybe we have sun, or if it is during the period of time that it's windy, so maybe we have more green power. But during the night, maybe we don't have because we don't have sun, maybe we need more brown sources to be used for power production. Now going to the methods to measure energy consumption. Actually, we have two different kinds of approach, and one of them is top down and the other one is bottom up. When we talk about top down approach, it's this approach is based on the total historical estimates. It considers factors such as real energy consumption data over a specific time divided to the total data processed, or maybe transfer data, or maybe the number of the users. Another one is bottom-up approach. It means that we need to consider and sum up the components that they consume energy. And of course, they produce CO2. They have CO2 emissions. I want to talk about the components here. I want to see which components we should consider. Actually, it's important to know the components to understand it, to understand the CO2 emission, and also to find out the strategies to reduce the energy consumption. So here I have almost three categories. The first one is related to the encoding and storage. Of course, we have video that we want to encode and we want to store that. A big part of energy consumption is regarding to this encoding and storage. Then we have our network. You know, the data intensive applications, they are increasing. The number of users and devices that they are connected to the network, they are increasing. So it's what challenging this thing is serving this increasing traffic demand while maintaining the sustainability. So we have video packets that they travel through the network, through the core network, and then we have access network, and we have edge components. For example, here, the things that we can consider, they are, for example, routers, switches, even the distance, the quality of the connection, congestion network that we have. For example, packet losses. These all could affect on the energy consumption. Another thing about the edge component that I can mention is about the CDNs. And as you know, they are distributed geographically, and they cache the data. And the thing is that they also have some operations, and they also store data, so they are consuming energy. Then regarding the user side, we can tell that we are decoding the video, we are displaying the video, and there are many things that we can consider here, from the having more energy efficient device, more energy efficient software, and for example, the display or the screen that we are using, even the brightness of that screen, and even network interface card, because network interface card connects the device to the network, and the data is transmitting there. So this is also important and should be considered. Of course, we may have more components, or but the thing is that we should see which one is consuming more, which one is maybe more important or more significant that we consider them. And just a very short values from the report shows that the data centers and networks accounted for approximately 0.9% of energy-related GHG emissions, and end user devices, they are responsible, or 72% of the energy that is consuming for video streaming is by the end user devices, 23% by data transmission, and 5% by data centers. Here I have some tools that we can use them for measuring the power. So some of them here, they can be used for the server or the PC things, and some of them could be used for smartphones. The one that we use in our project is Rappler, and also those that we are using. I would also like to mention two surveys here that they are very nice, and they really surveyed the tools that could be the first one. As you can see, it has a survey of tools for cloud networks, and the second one here is a survey of tools for mobile devices. One important thing is that even monitoring the power is consuming energy, so it's also something that we should consider. Talents and strategies. I will go through each of them, and I will try to give some ideas about how we can reduce energy. For example, here, I hope that we have time. Yes. Okay. The first, something that's important that I would like to mention for video encoding is about the compression algorithm complexity. This complexity when increases, so of course we are using more energy, maybe with more complexity, because with having more advanced encoding algorithms, maybe they are more complex, and they are encoding or compressing the video more, but they are more complex, so they are using more energy. So one thing that we can do here, of course, is selecting the more energy efficient codecs for energy efficient codecs. And another thing is optimizing the parameters. It also a lot helps for maximizing efficiency. And another important thing is efficient transcoding technique, because when we are doing transcoding, we decompress and compress. So when first we are encoding the video, there are some valuable information that we can extract, and using those information, we can transcode faster. And this faster thing help us for less energy consumption. Then checking the data centers. As you know, for ABRs, we encode the video, we encode segments and store them. We encode segments in different resolutions and we store them. But several research show that many of them, they are not requested. So that's the reason one solution could be on-demand segment encoding. So we just encode them when we know that they are requested. Another thing is about optimizing video bitrate ladder. You know that with the representations that we have, some of them perceptually are close. So maybe we can eliminate some of them. And another approach that could help with this optimizing bitrate ladder is per title optimizing. For example, you can see if we have a cartoon, maybe we need less representations for our segments, but if we have movie, maybe we need more representations for that. So this is another thing that we can consider. So we can have some energy efficient video encoding task schedulers to distribute segments among different, for example, instances or resources from the edge or from the cloud. One thing that I would like to mention here is that it's important that we consider suitable cloud services, the ones that they are using more energy efficient hardwares and softwares and cooling systems, for example. Another important thing is low carbon cloud regions, because you know that sometimes we are consuming the same energy. But if it is, for example, in Austria, or if it is in Germany, the CO2 emission is different, yeah? Because of the carbon intensity, because of the, if they are using their green or brown sources to produce that power. Another suggestion could be having, you know, that many of the cloud services, they have their pricing options, for example, is based on the time or based on the utilization of the devices of resources. So another solution could be energy-based pricing for the clouds. One other important thing here that I would like to mention is about the idle resources, that they are idle, but the power that they are consuming also is very important and should be considered. And many of the researchers, they are not considered actually. Then going to the network, when we have, if we reduce the bit rate, so we are reducing the energy consumption in our network. But how? Sometimes, for example, if we watch a video on a smartphone, maybe we cannot understand the difference between the resolutions or high resolutions. So maybe we can reduce the bit rate to transmit. Another solution could be path selection, because the channels or network channels that we have, it's very different if we are using, for example, LTE, 5G, Ethernet, and yeah, it's very different. So we can maybe select which one it's using less energy, and this way we reduce the network energy consumption. Another important thing that is consuming a lot of energy is CDN. And you know, with CDNs, there are sometimes that there are some cases that we have sudden surge in traffic. And in these cases, for example, CDN servers, they connect to the external physical servers, yeah? Or there are sometimes that CDNs, they are interconnected. And one of the CDN, for example, it can, one CDN can deliver content on behalf of another CDN. And it's like multi-CDN. So this is very difficult to measure the energy in these cases. It's like a black box. One other important things that I should consider is about the efficiency in CDNs, because generally when we are talking about the metrics about that, we are talking about, for example, the percentage of requests for which the request content is cache of the CDN server, is in cache of the CDN server. But this, what does it mean? That it means that if we have more storage, so we have better CDN efficiency, yeah, or the hit ratio metric is better. But it means that when we have bigger storage, we are caching more data, so we are consuming more energy. And many of the things, many of the segments that we are caching, maybe we don't have any request for them. So it's not good. And another thing is that maybe we can cache only based on the request, even in CDNs. Then for end user device, some of the things that I have here, they are like straight. For example, choosing the energy efficient network interface card, or optimizing network setting, or energy efficient devices, even improving screen display technologies. The other things that I would like to mention, one is optimizing the decoding algorithm that could affect, and another thing is video playback, optimizing video playback. With that, I mean, for example, the buffer of the playback. You know, the segment size, the size of the segment, some of the research show that it affects on energy consumption. It affects on the network interface card. If it is smaller, we are using more energy. And also our playback, if it has bigger buffer, it can fetch, for example, more segment in one transaction. So in this case also, energy reduces. One other very interesting thing that I would like to mention is about raising awareness of environmental impact of video streaming among users. Actually, research showed the willingness of the people to slightly compromise in quality of experience to reduce their carbon footprint. And it's actually very interesting. So if we try to learn the people, so it could affect. Here, I want to mention another important thing, that is these components, they are interconnected with each other. So we cannot just take a look at one component and reduce the energy consumption on that. What does it mean? For example, for the encoding part, if we use less complex algorithm, but our video is not that much compressed. Okay, so the energy consumption for encoding is decreasing, but then we are sending more data through the network. So the network energy is increasing. Okay, if we use more complex encoding, and on the other hand, we are reducing the energy consumption on the network, then because we are using more complex encoding, we are also using more complex decoding. And imagine, we only encode once the video, but we have several users, maybe many users, yeah? So I want to tell that they are interconnected to each other. And the important thing is that we should have a system. We should look at the whole system for any strategy that we want to use. There is also one suggestion, research suggestion, that they were trying to add some metrics and getting logs during the network and encoding and decoding for energy. That's very interesting, but also yet we should be considered that logging and these energy measurements also, they are using energy. I will go to the publications. I don't want to explain them. Just I would like you to mention, if you would like to know more about the challenge and opportunities, we have something published for that. We have also the match approach, and this is actually considers how to schedule our video tasks, video segments among different resources. And it could consider both cloud and edge computing instances. It tries to reduce the energy consumption. And then we also have a player, Echo Player, that is implemented by Bitmomin. They have also another work that it's related to the role of preset selection in per title encoding, and it actually helps for optimizing bitrate ladder. So just concluding the main remarks here, I talked about several key aspects that we can consider when we are designing and streaming approach. And I talked about how we consider components for accurately assessing energy usage. And I talked about some strategies that we can have for energy consumption. I also talked about these that we should consider a holistic system for reducing energy. And another interesting thing that at least it was interesting for me, that was increasing awareness of the people about this environmental impact of video streaming. I also introduced some measurement approach and tools. Thank you so much, and I will be so glad to hear your feedback, your questions.
Thanks a lot, Samira.
Thank you.
So we have time for some question. No? Christian.
Okay, so thanks. First of all, thanks for those interesting ideas and thoughts. I think there's a lot of things that we can do. Now, my question for now would be, you showed that there are many possibilities where we can start to do some research on and where we can find energy savings. Which one of you do you think has most potential and why?
Actually, the ones that relates to the devices has a lot of potential, because we have several and thousands users, and we are encoding once, but we are using it several times. This is the one that I really think is very important, and it could be from the algorithms, for example. Reducing the complexity of the algorithms is something that we can do further, or optimizing the ones that we have. These are, I think it has a lot of potential. Then maybe after that, I think about the data centers. And maybe you tell me that, okay, so for data centers now they are improving a lot, and they are using more energy efficient hardwares, even their energy that they are reducing, even they are increasing. That's completely correct. But when I am talking about data centers, I'm not only talking about the energy consumption, also about the CO2, because as I mentioned, okay, if we are using the same energy in two different regions, but the CO2 is different. So I think it's also important that we consider the data centers. In the research also, if you take a look, you see that many of them, they consider only the device part, because the reason that I explained. And I really think that, yeah, that's correct. Maybe the users are the most important one, and then could be the data centers. And the most challenging part that just I remarked at is the CDN, because that's a black box. And how we can measure the energy and what we can do for that part is really challenging. And I think there is a very good topic working on these parts.
Yes, thanks. And then you said that you are working on, and I think you showed a quick slide on that green streaming solution that you have, and I think which is also one of the main goals of your project that you're having. Now, yeah, exactly this one, where you had this video. The next slide, please. Yes,
This?
the eco player. Now it seems that is this what your main target is, to create such a green player that people could use? What is the state of this project, and did you already do some comparisons with actual players that people are using?
This one now it is implemented, and we are working on the model, end-to-end CO2 emission model that we are working on that. It's not compared with any other player yet, but we have started to check what is the subject reaction to this. For example, European people, they really like to select it for eco mode. They really care about that, I mean. Yeah, that's the state. Now we are working on the model, and we are going to implement that model to these that you can see.
So actually, if I would like to, then I could download this player and use it for myself?
Probably yes. Yeah, because
Probably,
now
okay.
we are
If so,
working
it
on
would be.
that, but yes.
Okay,
The
so
goal
if though
is
that,
that.
I think that would be interesting. It's very nice for some research on that. Thanks a lot.
Thank you. Thank you.
Thanks a lot, Samira. Just before going to the coffee break, we would like to make an advertisement. Since Samira will be is involved in a similar workshop tomorrow or this morning, I would say for you, in the context of ACM conference in Vancouver. So we just show you the program of this workshop, and would like to make a bridge between the two workshops on the two different continents.
Now I hope it's working, that I get that.
We just need 2 minutes.
Yes, I wanted to have 2 minutes for this, so I'm really hoping it works, but I'm not sure if the technical stuff needs to change the screen sharing so that it works. Yeah, here we are. So in fact, it was quite a coincidence that we have a very similar workshop at almost the same time on a very, very similar topic. And now where is it?
One thing, could you also share that? I can also see what you are showing. Thank you.
All right, yeah. Here we are, yeah. Sorry that I did not prepare that well for this. So we have this GMSys workshop on ACM conference, which I really like that we have that because it's raising a lot of awareness, not only in our community here where we're talking about that, but which is going to the ACM. And that will be, in fact, in Vancouver, where it is right now, I think 2 or 3 a.m. in the morning, and Samira is joining us here, which I think is really, really cool, and I'm very glad that she could do that. Otherwise, of course, it would be great if she could be with us here. But, well, this workshop will be exactly tomorrow with some topics which are very much related to what we are doing, so I'm glad if you also have a look at that, especially also because I'm also having some contributions, so it will be similar for me tomorrow at 2 a.m. in the morning that I will try to be there in Vancouver. And the both of us saved a lot of carbon emissions by not traveling to this place, and me not to Vancouver, she not here to Rennes. So we're really trying to work on this and to be energy efficient. So this is just for your information. And now, yes, we are open for some discussions in the coffee break. And we're looking forward to the next sessions.
Samira, do you hear me?
Thank you. Oh, I was muted. I was just telling thank you and bye for now. I will try to be there for the panel discussion.
Yeah, but we would perfectly understand if you want to to sleep a bit before the workshop this morning. So feel free to leave. It was a pleasure.
Okay. Thank you so much. Thank you.
Salut. Oui. Tu viens manger quoi ce soir? Oui, mais je sais pas où. Mais je vais réserver. Ah ouais, super. Ouais, mais c'est parfait. Est-ce que tu as du HDMI sur ton...
Je pense que je n'utilise pas souvent cet ordi.
Ah, c'est de l'autre côté.
C'est ça? Mais sinon, on fait comment?
Peut-être. Tac. Ouais, c'est ça. Tac. Ça va arriver. C'est bon. Parfait. Oh, attention.
Ah oui, je dois...
F5.
Qu'est-ce que j'ai fait? Bouge pas. Je sais pas. Comme ça. Ah oui. suis fatiguée, il faut que je ferme.
C'est là?
Des trucs là. Oui, je pense que c'est ça.
C'est bon comme ça? Ok, parfait. Bon, est-ce qu'on le
Je
laisse?
laisse ici? Oui.
Ouais. Ok, parfait.
very difficult. The energy consumption depends on the size of the data set, the processor, the type of hardware. It's very volatile. It's very volatile. The parameter size, task complexity, at the same time, special optimization, technical implements. Today, I would like to discuss an important topic for reducing energy consumption in artificial intelligence processes and deep learning algorithms. My name is Angelis, and I'm doing CIFRA practice in collaboration with Huawei University of La Rochelle. CIFRA is which is a state agency with tools employed in France. Ambitious role in artificial intelligence, such as in the algorithm, such as taking contact after employment, classification, mail classification, and so on. They are trying to materialize this independence. My test is the field. As the field, the artificial intelligence continues to evolve and expand, it becomes a crucial part to address the environmental impact of these models and the energy efficient. Now the state of the art freedom. It's highlights the importance of considering comprehensive we need to understand also the state of time faces the need to ensure to measure algorithms system and key performance indicators can be constructed. The indicators explores. Furthermore, it explores. Furthermore, it explores the key performance indicators, KPIs, can be constructed to evaluate and monitor sustainability. Here I can see in the graph. Very recently computed. In the graph, my thesis. You see. My thesis and how there various actions can be taken, can be implemented minutes. Oui, c'est bon. Oui, bon, je pense. Bonjour. Bonjour. Tiens.
Ça va bien se passer.
I need to speak in English.
Yes, please.
Oui.
Easier for me, otherwise.
It's okay.
You speak French very nicely.
We should not begin with technical terms. I think that would be a myth.
From which country? You're not from France?
Romania. Mais I live in France depuis. I'm living here from 15 years.
Where are you?
La Rochelle. La Rochelle? On the seaside, Atlantic seaside. Between Nantes.
Not that far from here.
Oh, 3 hours. D'accord. Thank you.
Okay, so perhaps you can start the next session. So the next speaker is Angela Sioka. Yeah, and the title is Towards Responsible Artificial Intelligence. So the floor is yours and you can start. So the mic are over there. Thanks.
Hello, everyone. Today, I'd like to discuss an important topic of reducing energy consumption in artificial intelligence algorithm, plus precising in deep learning algorithm. My name is Angela Siokan. I'm doing a CIFRE thesis in collaboration between Pôle emploi and University of La Rochelle. Pôle emploi is a state agency that deals with employment in France. But they invest a lot in the artificial intelligence algorithm. They will try to implement the ethical, sustainable algorithm. And today it's very important for us to take to reduce the energy consumption of the algorithm. It becomes crucial for us to address the environmental impact. The state of the art of AI highlights the importance of distinguishing between the training and inference AI system, and it emphasizes the need to measure the consumption of the algorithm. For that, we need to implement the measurement tool and evaluate the KPIs for monitor this consumption. We can act in training, in hardware, in inference, and in algorithm. The aim of my thesis is I focused in my thesis in the part of algorithm inference. I want to compress the algorithm and they measure them. The conclusion is that we need the smaller and faster model. We need to measure. Of course, we need the processor energy efficient. There are many methods for reducing energy consumption, compressing the algorithm, using the processor more efficient, optimized model hyperparameter, and the architecture of the model can make the distinction. We can use convolutional neural networks instead of recurrent neural networks for reduce the consumption. Here, there are two methods we can use for compressing the algorithm. Pruning, we can remove unnecessary weights from the model, remove the connection or the entire neurons, and quantification represent the weights of the model in the fewer bytes. In the graph, we can see my thesis, I want to act after the training for compressing the model, and I implemented Power API for measuring the prediction of the model. Another method is the distillation. Here, they are the method, knowledge distillation. We can obtain the smaller model from a greater one. We can improve. By pruning, we can improve also the performance of the model. We can reduce the size, the complexity, but also we can improve the performance. Because we remove the unnecessary connection with neurons. Pruning is a method that is used for pruning the weight at the neuron. Here is a graph. We can see a model a pruned model. And we can make pruning during training or after training. The question is, what type of part should cut? It's not very easy. It's not very easy. We need a reflection. Many processing, many training for arrived further that, make that. And the problem is when we prune a lot, we can lose the accuracy of the model. For the quantization compression, we can reduce the parameter precision. We can reduce the memory footprint of the model. And we can reduce the energy consumption. Quantization, we can make during training or after training also. And for knowledge distillation, today I'm making knowledge distillation for Pôle emploi. It successfully applied to compress BERT models. This method transfers knowledge from a large model to a smaller one for reducing its size. There are the limitations of this method. We can we can lose the performance if we delete too many parameters, and losing of accuracy. There are trade-offs. We can make a trade-off between the performance of the model and the energy reduction. Now we want to present you the measurement tools. For understand the measurement tools, we can make the difference between the physical tool and the software tool. Physical tool, it measures the actual consumption of energy, it measures voltage and the current, and it calculates the power of a multiplication of two values. But the software tools is implemented, is a sensor which is implemented into the hardware, and formula which can make the prediction of the consumption. The sensor collected data, and the formula, which is an independent software, calculates an estimate of power consumption. For this thesis, I have chosen Power API measurement tools developed by INRIA. Why? Because it is flexible, and there are a large community who innovate each year. Power API permit a holistic view of the AI application, but it's not very easy to implement. We need to know the hardware, the knowledge of hardware for translate the data, for obtaining the knowledge, and for calculate the KPIs. For Pôle Emploi, today I work in NLP, in email classification. Il use un BERT model, Flaubert, qui est un transformers for French. And I compression the model, and I implemented a measurement tool, and I write rules of good practice. This year, I make an experimentation with LSTM architecture, the model. I measures with Power API. And I use two techniques for compression, pruning and quantification. And today I'm working in Flaubert for email classification task. Flaubert is very large, and I compress by knolling distillation and pruning. After that, I need to measure that. Here, a few results. LSTM model with a database in open source, ImageDB. And I used 4 models, and I applied the pruning, quantization, pruning and quantization. And I make the prediction, and I measure each prediction. Here we can see the consumption versus the number of parameters. And 4 models. A model is very large. We can see the energy consumption is very high. Here, say for experimentation, I trained a BERT for an open source base, the same base, database, and I measured the energy consumption. The BERT versus distilled BERT. BERT base it had 110 million parameters, and distilled BERT 66 million parameters. Of course, with the accuracy almost the same. And today I want to make the same for a Flaubert, the image classification task. I want to distilling, and after that I want to measure. It wasn't very long.
Okay, thank you so much for the presentation. So, is there any question in the audience? Any comments? Okay, 2 questions.
Yeah, thank you for your talk. It was really interesting. I'm Alexandre Merca from Tampere University, and I have the 2 questions. The first one is about the compression techniques that you are using. Are you aware of the neural network compressions and representation standard NNR that was developed by MPEG a couple of years ago? Because that standards include, from what I remember, include this kind of pruning and other compression techniques. So I was wondering, did you try to compare your results with this compression standard?
Today, we not found the measures for AI algorithm.
Okay.
I can't compare.
Okay, but just take a look at some point of this standard, NNR, and maybe you can extract some relevant information from that. Okay, and I have the second question, but this is quite really techniques, and I don't know, maybe someone else can have an opinion on that. But at the beginning of this presentations, you say that the energy costs come from the DRAM mainly, about the hardware part. So it's memory access to share data from to access the data from the memory to the processor. And I was wondering about what will be the impact of this new technology called RRAM for resistive random access memory. That currently they announced that they're able to reduce the power consumptions of 20 times with that new memory. And now I'm wondering then when this kind of memory will be available in the market, maybe like in 3 or 5 years, how that will change these energy consumptions of this kind of inference. But I don't expect that you have the answer, but I'm just curious of these kind of things, just to see if it will change the game, and then if we also should take into account that in this kind of research.
Here. My thesis cover this part, only this part, inference and algorithm. We can find the hardware, accelerator, CPU, GPU, but I want to focus in this part. It's very, it's very large area. We can make a lot of things. But Pôle Emploi, the company, they don't want today to invest in processor, in the processor. We can use the code, not a lot of code. We can reduce. We can invest in the processor, of course. We can act in this 4-part phase of AI systems. We can make a lot of things, of course.
Okay, thank you. There was another question just behind, still, or?
So I wanted to talk about also the hardware. So I clearly understand that you cannot invest in CPUs on specific hardware, but nevertheless, GPUs are critical right now for doing training, but also inference. And they had GPUs in also very common processors. On these architectures, and also TPUs can be really cheap, and it's really the future of inference. I think
I'm aware of that.
Yeah, but the question is, these kind of hardware have constraints. You cannot put any kind of computation inside. So they define a framework when you can define what is possible to optimize or not. So did you plan to check what are the hardware constraints? But because you can have the full order of magnitude of power reduction with this device, with implementing in the right way. So if we can extract from the hardware what are the good features to implement, you could drive better the optimization you are driving. For instance, one of them is obvious is using FP8, so the reduction changing the quantification, but also there are reduction.
FP16.
FP8 is using a lot right now by Google, looks like, depending on what this is what they are saying. But also they are constrained on the data path inside the neural networks. So we have to comply to these constraints. So do you plan to have a look, not necessarily buy them, but have a look at what are these constraints?
It's just the beginning for Pôle Emploi. After that, they want to implement an accelerator for inference part. Today, train in GPU, but today he wants to measure more than act in processors, something like that.
Okay. Okay, thank you. Always surprising to see Pôle emploi working in this field. I have some, it's a bit striking, but anyway, thanks a lot.
They have a lot of artificial intelligence
Very nice.
algorithm,
Okay,
and
very nice.
visual recognition, email classification, putting the offer and the demand together for employment.
I was not aware of that. Very nice. Thank you so much. So we are moving to a new speaker. Who are you? Ah, Christian. Okay. So the title of the talk, I don't remember, so you are going to present a bit.
Okay, thanks. I'll try to connect and try to make it work. Yeah, quite optimistic.
Okay, go
Okay,
ahead.
thanks.
Thanks. Just wait a minute for Angela.
Okay,
Just wait just a minute for...
all right, good. It's not bad because I need to prepare. I learned that we need to dress up somehow at this conference. So I brought this green tie for today because it makes, I hope that people now think that I'm trustworthy and that things that I'm saying are important for, well, for research, for our society and so on. So I'm putting this tie quickly. So that, of course, it's green because we're about green IT and so on. And of course, it has nothing to do with greenwashing. I'm pretty sure that you're aware of that. So today I am not showing the title at the beginning, but something that I looked at or that I would like to point out in this thing. So we heard that sometimes today that end-user devices are quite a large part. And I heard people argue that the top left one, where we are sitting in front of a TV, 8K and big, is maybe not a good idea, but maybe something with a lower resolution, like at the top right, would be better, or instead of having that big TV, you could use your smartphones. But in the end, it will all end up, if we are really honest, it would be definitely better to read a book. But still, we have all these other possibilities, and let's try to see what we can do. And with this respect, I would like to talk about the topic of joint QoE and energy optimization in video communications. Because in the end, well, we are engineers and we've always been struggling to increase qualities, to have a better experience, to make people satisfied. And of course, this does not work at all if we do that over and over and over again. So we had some, let's say, analysis, a little bit of studies on this joint quality of experience. I was very happy to see this morning that there are other attempts like this greenness factor, which in fact can increase the greenness or the perceived quality if people are aware that they are ecologically, that they have ecological choices and so on. But there are in fact many things that we could do, and I would like to give a quick brief overview of this, what we have. So we know that video streaming is everywhere. I just noticed again this morning in the metro that there were 100 people and 99 of them were only watching their smartphone. So it's well, we're living with that. This is especially the smartphone case. It can happen, and often that we have a low battery, and it still happens to me. I was just making sure that my laptop is still working by plugging it in because I was not sure. So that is one reason, and of course also sustainability. Now, what we looked at were some, well, let's say straightforward methods to do that we could do with video communications, with video compression. And we looked at what happens if we scale, for example, the resolution, and we did some measurements. I know that we already had some results, but here it's a little bit of a saying it again, but I know that saying again and again and again is the best way to really learn and understand what happens. So we tested resolution scaling. We tested what happens if we reduce the frame rate. Then something that I found very, very interesting, we did some QoE and sustainability analysis on actual data sets that we could find in the literature. And some, well, we could say some potentials that we could have with all these ideas. So the first thing that we looked at was resolution scaling, because in fact that's very simple to do. Also to to analyze and to see what happens. Because if we want to compare the quality of videos, we usually do it frame by frame. And with resolution scaling, we can just downsample a video, we can do some compression and all the chain, and then we can rescale back with very simple methods and measure the quality, and we can also measure the power consumption, for example, of a smartphone, which we did. So you can see that we have, let me see if I have a laser pointer. Yes, that is here. So this is our video. We did some spatial downsampling with a certain factor. We used some encoding with a quantization factor or a CRF when you use common encoders. And then we transmitted this video to a smartphone, which had a very regular player installed. It did the decoding, it did an upsampling to full screen. So we just assumed that we want to have full screen. And then we can find out about the power and we can find out about the quality. We could also measure, but measuring is energy intensive. And if we have a model which is quite accurate, we chose to use the model first, at least for this study. But in fact, it is very, very close to reality. And the result would look like this. This is something where we can see the quality vertically. This is the PSNR, a very common quality metric. The higher, the better. 38 is very good. 26 is bad. And we have, in this case, the estimated power consumption of a smartphone, of a very regular smartphone it was actually my smartphone back then. So we have these estimates, and these curves represent a single resolution that we used. So the very top curve, this blue one with these crosses, this corresponds to the original resolution, which has been encoded with different quantization parameters and bit rates. And we can see for each of these coded sequences, this one and this one and this one, the corresponding power that we need on the smartphone, as well as the quality. This one has a very good quality and a very high power consumption, apparently. If we go to the bottom left, we have, of course, the inverse. We would like to be up here, 38 at 1.8 watts or even less. But physically, as far as I know, this is at the moment at least quite impossible to get, but we can try to get closer to that. And what we found is that if we do some scaling, we can actually be better at lower qualities, but that might be sufficient. Why not? Why? So especially if you go for TikTok, if you have seen the videos, they are shitty often, the quality is awful, but who cares? So in these cases, it might be a good idea to not send a 4K or HD sequence, which is, I think, not what they do, but this is the proof that why they not do that. But you should send a lower quality, like here, because you would save power, in fact, by the same quality. So here at a quality of 30 dB and a lower resolution, you have a lower power consumption than if you would have the highest resolution. The reason is just that we process less pixels, which is quite common and easy to understand. And this is something that in fact works. Then, of course, nowadays we're more about perceived quality. So we have fancy new metrics. One is called the VMAF score. People from video compression are very aware of that. And this fits even better what we can see. And especially on a smartphone, you would see that the highest resolution here, which was an HD one, does not make sense at all. So 100 would be perfect. That is somewhere here. And even at a lower resolution, you would see that you can reach almost this score of 100, which is perfect quality. So looking at this, it's become even clearer that people should never use HD on their smartphone. It does not make sense. Don't try to do that. It does not help anyone at all. Good. So this was about resolution. Then the next thing that we tested was, which is quite straightforward, I believe, frame rates. What happens if we send less frames than all the frames that we have? We can have 30 frames per second, nowadays 60, sometimes even 120. I think my newest smartphone covers 120 frames per second for whatever reason, I don't know, but it can. but we could reduce the frame rate and see what happens. So we did that. That was a quite recent work that I will present, in fact, tomorrow at GMSys, the one that we talked about today, before, in Vancouver. But we did some downscaling with temporal downscaling here. We also tested some filtering, which did not really work. And we did a similar thing as before. We did some encoding, and afterwards we compared the quality with the original. Now, a big problem with quality measurements is when you do some frame rate downsampling, that current metrics that we have, they do not care about frame rates. They would only compare 2 frames, and anything like motion is hardly included. So it's a little bit tricky, but we were quite happy that we found a metric which was quite recent. I'm sorry, I should have put the paper maybe. It is called GREED, G-R-E-E-D, this one. And this, in fact, was trained including frame rates. So it can know if you go up, down from 30 to 15, and you know about the frame rate, then it would include this into its quality evaluation. What is also a little bit strange, but that's how they defined it, is a lower score is better in this case. So 15 would be a better quality than 50 up here. But the bad thing here is that it's not really clear what happens and if it is a good idea. So if you would ask me, should I downsample my video, then I would say it depends. That is different from resolution, where it was always quite nice. Here it really depends on the content, of course. It depends highly if you have content with a lot of motion and there is happening a lot, or if you have a static scene, for example, this slide. So if you show this slide, please use a frame rate of 1 frame per second maximum, maybe better less. But if, well, it was a video of me and I was dancing some song that people watch over and over again, then it would not work, of course. So it depends, and we can see by these lines that in fact it depends. So this is a typical video from BVI Bristol dataset, quite well known, bobblehead with a lot of motion, high frequencies and so on. Highest pulse qualities will be the red line right here. And if we downsample the frame rate, which is the blue and the green line, we can see that the quality will drop extremely. And you can easily perceive that. If we have a very static scene, so this is the other extreme example in the center, then we can even increase the perceived quality because the encoder has much more sources to encode its video, and it will tune its bitrate and so on in such a way that the quality of a single frame is even better because there are less frames to be encoded. And this is why we can even increase the quality right here, which I found quite nice to see. But unfortunately, we do not know beforehand. So this is another water splashing, another thing. By the way, this is the bit rate, but here is the figure for the energy, which is quite similar. So here we have the decoding energy on the horizontal axis, the quality on the vertical axis, and we can see that we can always have energy savings. So that is for sure. If you don't care about quality, you should do that. But even here, in very special cases, you can have both quality increasements and energy savings. And just to be complete, these are the examples that we used. This is 1 frame of the bobblehead sequence. This is an original one at 120 frames per second. This is at 30 frames per second. And it's, I think, quite easy to see that here you have a lot of structures that are moving quickly. And of course, reducing the frame rate, they will all get lost. And this is reflected by the score. This is the other example. It was a guy playing a guitar and nothing was moving except for a little bit the hand and of course the strings. And that does not really have a big impact on your perceived quality. Well, if we believe that score, of course, that's always another thing we need to take into account. So these are 2 examples for resolution and frame rate. And then we can even go on, and we found that in the literature, we can find very much information on streaming and streaming behavior, which is very, very interesting. So there is an open source crowdsourced dataset from YouTube, not really the newest one, I think it was for 2018, but real data. So people in Germany, they used YouTube and they gave a lot of information for that. They gave information on what kind of video, resolution, frame rate, bit rate. They had scores on the codec that was used, even the device, and we had values for desktop PCs and laptops. And that is very interesting. All in all, we had almost 500,000 of entries right here of this database. And we wanted to find out, can we use this to find out about quality of experience and the energy consumption? And then again, we have to speculate, of course. So we learned today, this morning, that speculation is a very important part, but it is close to what we have in fact. First of all, we can speculate about the quality that we perceive, and we have standardized models for these speculations, which are quite accurate, in fact. This is an ITU-T recommendation called P1203. Very interesting and nice. And, well, we can do the same with the power. We have very nice power models, which in fact use exactly the same parameters. So these parameters of bitrate, resolution, frame rate, stalling, codec, and so on. And from these parameters, we get very accurate models and ideas on how much power is consumed on a device. Now, we did not measure all the devices of the participants of that crowdsourced study. I don't know how to do that. If you can tell me, I'd love to know. Would be great to do. So I used exactly this laptop here, did some measurements and said, well, it's representative, so let's take these numbers and see what happens. That's the speculations we did, and I think it's quite okay. And this is, first of all, the measurement results that we used for modeling. So here we have some results for a codec H.264 on a desktop PC. We tested different frame rates up to 60 frames per second. We used different resolutions from, this is 1080p, so HD, to very low 240 pixels in the vertical direction. And this is what you would find at YouTube, so depending on which values you have. And then we have all these lines in different colors, and they have got a certain width. And the width represents the difference in bitrate that we could see. So lowest bitrate to highest bitrate and the difference. And here we can see that the frame rate has got some impact, quite a large impact, from 75 to up to 90 watts. Resolution has got a little bit of an impact, not as much, and bitrate also. But this all adds up, and this can all be used for power modeling and for optimizations. So we trained a model with that, which is quite accurate. We trained 4 models because we had 2 kinds of devices and 2 codecs. So we had H.264 and VP9, we had a laptop and a PC. And the first thing that I found really, really interesting, I did not know before, I did not expect that, and this is very nice to know, is I always thought that one codec is probably more energy efficient than another. H.264 is very well established. We have that for 20 years, and all the devices are optimized for that. VP9 is also quite old, but not that old. And, well, YouTube uses this nowadays a lot, but it's still not that common. And we found that on the laptop, H.264 was much more energy efficient, 14 watts versus 18 watts minimum. On the PC, it was the inverse. It was definitely by a coincidence, I'm pretty sure. Still, I like this result because it tells us that there's a lot of things we do not know. It's a lot on implementations. Which software do people use? Do they use hardware decoding? And so on. And that is something that the sender side does not know. It can only send you a stream, but it would not know what happens on your end user device with that. So these are the models that we found out. And this is in fact the result of the crowdsourced study. So this is a scatter plot. We have a lot of points, 500,000 points in fact. So these black points is each one streaming session. We calculated the average power with our model on a PC in this case. And we calculated a MOS, so mean opinion score, a quality of experience, a quality metric for each of those sessions. And found that many of those are really not optimal at all. We want to have a high MOS score, something like here, and a low power consumption. But a lot of them are landing somewhere here in between, which is definitely not optimal. So we found that, in fact, in practice, there are, without changing the quality, without having something like a sufficient quality, we have something to optimize. And that we do that, have that for laptops, for PCs, and for different codecs. Still, of course, you can see up here where it is getting brighter. This is a point where we have many, many sessions. So this tells us that we are at a good point. It is very close to the optimum at the top left, but still that there is some room for improvement. So we did some speculations and thought, okay, can we make this better? We could say, let's keep the same quality and choose the parameters, the bit rate, the frame rate, the resolution in such a way that we still have the same quality. So we would move all these points, all these sessions to the left, and then we can calculate how much power we would save on end-user devices. And these are the results. By this, we could reach power savings by roughly 5% for this complete data set, which I found quite interesting. Of course, again, it depends, and there are some assumptions, but this is something that is, I think, quite realistic. Then we tested other things. For example, we had something that we try sometimes today. What happens if we are happy with a lower quality? Can we even increase that? Are we happy to have a lower quality of that, and we accept that? How much would we save? If we do that for the PC and the laptop and so on, we would say that we restrict our quality, our visual quality, to a maximum MOS score, for example, 4, whatever that would mean, I don't know. Then we would save another, well, let's say 1%. That's not too much, but it's something. If we go even down to 2, then we would have 3 to 4%, which is, okay, it's something, but I think 2 is a very, very bad quality. So I'm not sure if that's a good idea, but this is the potential. We tested some more stuff. So this is, let me see, if we switch to the different codec. So if we knew, for example, on my laptop, we should choose H.264, so we would only stream H.264. So on this laptop, we would have relative savings of 26%, which is quite a lot, in fact. On the PC, it's just 13% because we have a higher offset, the offset power. And then we try to do all of those stuff. We did not only change the codec, and we said we would change, we would have a maximum MOS score. We also tested what happens if we tell people, do not use your desktop PC, but use your laptop. And do not use VP9 on your laptop, but use H.264 on your laptop. So we switched and calculated what would happen if we moved all these desktop people with VP9 to the laptop with H.264 on the complete data set, just to know what happens and what we find. And in fact, if people would do that, we have some significant energy savings. What would be expected, and what I would now repeat, please, people, if possible, do not use desktop PCs, do not use TVs. Whenever you're watching things or when you're doing your calculations at home, laptops are in most cases absolutely sufficient to do that. And this, in fact, makes a difference of more than 50%. So that would be the wrap up of what I wanted to talk about. So we try to find out about this QoE and power consumption, of course, only on end user devices, a little bit restricted, but using a lot of data from the internet and from crowdsourcing, we can find that we can, in fact, save some things and have some savings. And as an outlook, there's also ideas that we heard before, but I find very, very intriguing. We can have looks at the holistic optimization of communications. What I really want to do is to look at what happens at spatial-temporal downsampling. So of course we can do both at the same time. Why not do that? And what we also did not look at here is the sender side with the encoding energy. And yeah, that would be all. These are some more literature hints. Thanks for listening, and I'm very happy if you can give me and my nice green tie some nice questions at the end.
Thank you so much. At least 2 questions, 3, okay. Okay.
It's me. You have presented the power consumption in
Yes.
watt. I
Yes.
have presented the energy consumption. Watt with a unity of time.
Right?
The power consumption is not the same with the energy consumption.
That's right, yes. So can you
The
tell me
power
on which slide it
consumption
was?
shows not showing we can reduce the energy consumption. Because if you have the GPU, GPU, accelerator, TPU, you can have the power, very high power,
Yes.
but you can we can't see that we reduce the energy consumption.
Yes.
Okay.
Yes, absolutely. So we have a big design space in this region, and it's true that's something that I'm always asking myself, should I focus now on power or on energy? And it's a very important question. I totally agree, and it's a good question. Now, I don't
know
remember.
it's very difficult to measure the
Yes.
energy consumption. Is this? I want to make a distinguish between
Yeah, I see.
my work and yours.
Ah, okay, I understand. So you are looking at the energy consumption. Okay. Yes, I think that in the end you are absolutely
Watt
right.
and joule, and not the watt.
It's right. In the end, it's important that we reduce the energy consumption. Because if we have a power of 1 gigawatt for 1 millisecond, we don't care. But we always have that multiplication. Now, I'm not sure what I had in my slides here as the metrics. What we thought about here is that if we're looking at video streaming, then we have a process that is running quite smoothly and that is running for a fixed time interval. And we don't know this time interval usually. We can have a look at a complete video, but if we have these streaming sessions, these streaming scenarios, we in fact had the information on how long it took, but the power model that we came up with, it is at the first hand sufficient to look really at the power, and then, well, if we have the time, we would multiply it with this time to get the overall energy in the end. And as we were looking at this static process, which is something which is, I think, more easier to understand and to optimize.
We need to show the time.
That's why here we first looked at the power, in fact. But you're absolutely right that the energy is what counts in the end. Thanks.
Thank you. Thank you for your presentation.
Thanks a lot. There is another question there.
Thanks for your presentation. I have a question about the temporal downscaling you did. Was it based on a temporal interpolation or just a decimation?
Yeah, that's a good question. Also, I'm asking myself what to take. In this case, we just averaged multiple frames.
Okay, so with an interpolation model.
It was an interpolation model, yes.
Because it's not what a common encoder will do.
Is it right? Yes?
Yeah. So usually an encoder received an input frame rate and just decimate.
So it was just take every second frame and encode?
Yeah, for example, if you receive 60 frames per second, you will output either 60 or 30 or 15. But you won't get 40 or 50.
Yeah, that would be the next question. Do you know what would happen? Because I can choose 40 by encoding. What would the encoder do in that case?
You can choose 40?
I think so, yes, and it would give you a 40 frames per second.
I think it will just decimate, remove two frames every 6 or something like that.
Okay.
But my question was more about the interpolation method, because if you interpolate images, you will have a different visual effect than just decimating.
Yes.
So the MOS will be different, I guess.
Yes, you're absolutely right. And maybe we could have, so we did some initial tests where I remember that we found that the interpolation gives a better quality in the end than decimation. But in fact, I did not check what typical encoders would do. So here we came up with our own pipeline. But thanks a lot for that remark. That's good to know for future research.
Thanks.
It's very helpful. Thanks.
Okay, thanks a lot for this presentation. It was really nice. I think I could ask you questions for 2 hours, so I will try to just focus on some specific questions. But the first one that came to mind when I saw that summary and these outlines is, what about scalability? Do you have any idea if scalable coding could provide something that could be useful to save some energy at some point?
You mean scalable by you get something like a bitrate ladder?
You have the base layer and the enhanced layer, and then you have this technology like SHVC for scalable HEVC.
Yes. Okay, that's a very good question. It's definitely something that would be interesting to look at. I just had the feeling that people are not really using scalable video coding nowadays.
Yes.
They find different solutions. So I didn't have a look at that because I had the feeling that it's maybe not that relevant. So
Yeah, but maybe for energy efficiency, it could become again more relevant. But I agree. I know that the community didn't find any way to use it efficiently. So
for energy efficient, the
Yeah.
idea is good. Yes.
It might be a good use case for this
Yes.
this topic, yeah.
Yes.
For
absolutely.
SVC, yeah.
We
So-
could try to have a study on that.
yeah,
That's-
let's work together on that.
Yes, absolutely.
I have a scalable encoder, so in open source.
Sounds good. Yes.
Okay, thanks.
Okay, is there any other comment in the room? No, so
Was there a comment? I'm not sure. Or was that just hi? Nice to meet you.
I hope you didn't answer already. It's about the hardware. I've seen 2.2 watts for the device, for the phone, basically. So you took the consumption of the phone as a whole.
Yes.
I've seen also between 70 to 90 watts for the PC, and around 30 watts for the laptops.
Yes.
You face a problem with a codec on the difference between generation on the device. We can have a proxy for this, which is the generation, because if you check the generation, so the ideal would be to know exactly what kind of hardware you have. And the hardware has a really strong influence on the power consumption for such purpose.
Yes.
And so it's difficult. You cannot address this globally, but you can have a proxy, which is a generation. And on the global market, when you have a CPU, if you have a GPU associated to it, you have decodec power efficient facilities that are hardware encoded. And if you have the software able to detect it, you can use it. So if you focus on the generation, you would have a reasonable proxy of the capabilities. So, for instance, you talk about a PC. The generation of the GPU use could be a big proxy for the power consumption. The same, it's even worse for the telephone. Sorry. On the telephone, depending on the generation, you will have strong differences on the power efficiency on the video decoding.
Absolutely.
So
Yes.
I would think that to using this proxy generation, so we have to find a metric for this. You could find a way to adjust your optimization depending on the kind of device, or even better, say, keep your old device, because with your old device you can achieve such a good satisfaction with such constraints without moving to a next generation. Okay. That was just my small remark.
Yeah, it's a very good idea, I think. I think we can extrapolate a lot, especially on the end user device side. And there's a lot of knowledge, hidden knowledge inside that we could quite easily use for such streaming scenarios. Thanks a lot for that remark. It's a good idea.
yes, then
Thank you very much. On that question, the effect that we see here on for the PC in the lower right corner, substantial difference. Do you attribute this entirely to the power consumption from the CPU, or do you think that the parameter change also affects any other part in the architecture of the system,
Yes.
like the graphic cards and other
Yes.
components?
So I can only, so we did not look at that into detail, but what we can see maybe derive a little bit is from these figures here. So especially maybe these widths of the lines can be interesting, because we can see that this variation, depending on the bit rate, is apparently for VP9 much higher on this case than for H.264. So I would assume that there is some more than only the decoding part behind that. But I do not have the detailed information for that.
Okay.
But I think there is more to it. We know that these parameters are all quite important to have a good estimate and a good idea on the power consumption. But the underlying reasons, that is something that I would like to understand more. But, well, if we're going for machine learning, maybe we don't need to. Maybe it's sufficient if we have this model and then work with it. Because the pipeline on the end user device is really, really complex. there's happening a lot from getting the bits and then processing the bits, then decoding the bits, and then reconstructing a video, then going to the GPU, then rescaling maybe a GPU and preparing it for the output, then having the monitor and the display and so on. So there's so much going on that it's maybe easier if we do some machine learning in this case. But still, I would like to know. I would like to learn more, and we did not look into detail while we have these differences here. There was not enough time, and we thought this is good results. Let's keep it.
And thank you. And then connected to this, there's a need for the community to also exchange best practices for measuring setup. Yeah, how can you distinguish power consumption of the network interface card and the CPU and the memory and all of these components? And how do you So we heard about RAPL versus external measurements. Big demand for sharing best practice.
Yes, that's true. That might be a very good idea in our community to have something like an outline or a best practice, I don't know, paper or technical document, because I think there are many methods out there and they all have their pros and cons, but it's not easy always to find out what the pros are and what the cons are and which one to use best in a certain case. And I would definitely agree it would be nice to have something like that.
Yeah, okay. Thank you very much.
We can work on that if you like.
Yes, yeah, that'd be fantastic. Really enjoyed this. Thank you.
Okay. Thanks a lot, Christian, for your talk. Very nice. So it is 12 o'clock, so we have time for a kind of panel, an open discussion, let's say for 15 minutes and so on. So I have a first, you want to say this? Okay, all presenters can come to the front, but there is only one, finally, two.
Do we have some more presenters? I think Eric is here.
Yes, Daniel, if you can come as well. Angela, if you want to join us as well.
1, 2, 3, 4. We could even sit down in a very special panel-like style.
Yeah, you're beautiful.
We will have Daniel join soon, right? He's just quickly. All right, good.
But my first comment was that for Daniel, unfortunately, but perhaps we can start with that. Since this morning, I'm a little bit confused, in fact, because there is a paradoxal situation. So many studies says that user devices account for a majority of energy consumption and so on. Okay. Can we solve the problem if we switch off all the user devices? No, because the infrastructure is energy consuming much more than the user devices. So I am a little bit lost. Finally, what should we do? Should we work on the user devices? Should we work on the infrastructure? Both, certainly, but I'm a little bit lost. So, yeah, I'm sure that you would have a comment on that.
So I think the climate situation is urgent enough that we should not choose. We should do all of it. That's my short answer. But it's true that if we want to start somewhere, it would be a good idea to start where most of the energy is used. And most of the energy is used in the home. And there's an awful lot of homes out there where the energy is used. So yes, that's an obvious place to start.
Okay, so I just repeat my concern, in fact, Daniel, because I'm confused since this morning and with your presentation as well, since many study indicates that the user devices account for a majority of energy consumption. So finally, perhaps if we switch off all the user devices, we could solve the problem or bring a new solution. Unfortunately, the infrastructure, even if the usage is zero, consume a lot. So I was a bit lost, in fact. What should we do? And the first answer of Eric was, okay, we have to work on every component in the chain and so on.
So I totally agree that if we take an instantaneous perspective on what will happen in the next hour after we turn off all of the user devices, we would still have the networks and the data centers running slightly, maybe consuming slightly less energy. That's the dynamic part, but certainly not zero. However, those organizations are only there in order to provide services, and after a couple of weeks, they would notice no one is using them, and they would also power down. So I think this is the important bit, that we understand really what is the medium and the long-term consequence to those organizations, and the interventions, they happen, of course, on the technical level, where we know what are some examples of medium-term changes. So caching behavior, for example, manifests in medium terms. This is purely without someone, a human, taking an intervention. But then, of course, all of those business decisions that engineers and managers, etc., designers, capacity planners take, they would manifest in the medium and long term. And to understand and understand the potential for reductions through certain interventions, we need to anticipate those savings by working with these organizations together and then thinking through the consequences of certain interventions.
Okay. And is to comment in the audience, please. Perhaps you can say your name and your company and so on.
Okay, so I'm Mathieu Muller from MediaKind. Especially, I'm working in the video compression domain. Just a question, general question. We know that the production of devices for even network equipments or user devices is a big part of the CO2 emissions today. So my question is, should we stop producing new equipment with new technology and just working with existing technologies?
Yes. Comment more. Okay, yeah, it's a very good question, but in many cases, I believe that in fact we're having good solutions which are working, and I'm a big fan of having devices as long as possible. So, like this exchange of smartphones every 2 years that has been imposed to us by network operators, it does not make sense at all. 2 years is nothing for a smartphone. Something like 10 years is definitely difficult because the devices will not work. You will have problems with technology, with batteries. You cannot exchange spare parts and so on. But it would be from 2 to 4 to 10 years. It would be a reduction of 5. And if everyone does that, we have a major impact by that. So I believe that is one thing that might really, really help. On the other hand, I think we should, in research, think, is it really helpful if we do some certain kind of research? So by talking about this, I think we have noticed with audio compression that we had MP3 that was important and helpful, and then we had 2 or 3 more, but people are not aware of that anymore. And nowadays, we don't care about it. People would send as much audio over the internet as possible, and there is no constraint in terms of bandwidth. So actual new developments in terms of audio compression, reducing the bit rate, has a very, very minor impact. And we are, I think, now at the peak for video compression, in my opinion, because we have the bandwidth for really, really great resolutions and quality. And now going even further to reduce further bit rates with very energy-intensive AI, I'm not sure if this is really, really helpful. So maybe I would definitely consider that in certain areas, we are at a sufficient criterion, we arrived there, and maybe we should focus something more on other things, like new techniques like AI. I was very interested to see that. That's very important now, because we will have that, and we cannot stop it completely, but we can make it better. And also, maybe also other visual types like point clouds or immersive media, which will probably come, and which is also, to be honest, better to have a full virtual conference with maybe point clouds, immersive media, and so on, than traveling all around the world.
Thank you very much. There's this nice question, so I can actually talk about my pet peeve. And that is indeed the life cycle analysis shows that, let's say, television, half the energy is used making it, and the other half is used when the consumer watches it over on average 7 years. And that's sort of true with all equipment. Half of it is spent before it even switched on for the first time. So if we all start to do research and we're creating new technologies that require the 1.6 billion TVs in the world to be replaced, we're probably not doing the right thing. Except if we say, and this is where I think regulation comes in. In Europe could conceivably do this. We could say TVs need to be updatable, firmware updates, so we can put new software in them when a new codec comes out that is better than the previous one. My pixels are still good. I don't want to replace my pixels just to be able to have the new codec. And I think the right to update should sit right next to the right to repair that we now already have here in Europe, which is a good thing. But that needs a government to step in, and I'm not a government, unfortunately. I would like to be for a day. We'll do it.
Thanks, Eric. There is another comment, perhaps, over there, or?
I would like to testify directly for the answer about the phone. I have a phone which is 10 years old and it's working fine, and I'm not having trouble with videos. I'm having trouble with OpenStreetMap because it's getting too expensive for this device. So I have a Motorola 4G, and the key point is I took the oldest device I have that has 4G interconnect. So there are critical hardware parts we need to have as soon as we have it, and we can have a device as old as 10 years old, and everything is working fine, and I can go and take it and show it to you if you want. I mean, of course, I've been fighting for the last 15 years to remove all Google's related stuff to my devices, but this exists. So if I want to connect the dots, so yes, another point, if I may, there. I try to connect the points on what I've discovered is in the last few days is a huge work I've made to scientists for making optimizations. We can really salute all the effort made, but there are still optimizations. On the video level, it's really huge. If we look at the trends, we see that the consumption part and the usage part is really decreasing. So the key point was the presentation this morning with rebound effect, clearly shown about infrastructure and requirements. It's something where we have to fight. So if I connect the dots, also I have connected up with the SHIFT project keynote, what we're saying about the business model for big techs, and also rely on that. So I think you have found, we have discovered that the job done is great. So let's take on this. New hardware, as the Swedish guy presented today or 2 days ago, all the devices in his house are not consuming much more. I would agree. I tried also. It's fine. So the rebound effect is right now the target everywhere. And it will have an impact on devices, on infrastructure through the loop of the months. So what I would say is, let's favor ad blocks. Let's favor all the behavior that will prevent the usage of more videos that are not required. I think it would be much more efficient than reducing the quality of the video. If we also work on alternative software stacks, when we could change business model. But to change business model, you need to create one. And here the scientists can provide way of managing hardware and infrastructure that could help the society build new business models. And I think it's a large research topic that could bring a big difference. The jobs here with these weeks show that we could do something at the end. So it's a bit an opinion more than scientific research.
So we are all scientists, quite difficult to change the business model of the big tech, but any comment on this point? Or
yes, we are scientists, but I think that if we want to have an effect, we have to work with people from other domains. I think, yes, we have to work with people from social science and to work together in order to have new economical model, to have regulation. I think, for example, in Europe, it will not be available. 8K screen will not be available because it will consume too much energy. And I think that only working with people from the technology will not solve the problem.
Yeah, most probably.
So there have been so many great ideas exchanged now. What we can do, where we can attack. I think it's really fantastic. But it's also possible that we lose sight of what to do first. I think I believe the lowest hanging fruit really is the slowing down of the metabolism the rate at which we replace our devices. And so, Eric, you mentioned that there is the legislator's role here, and probably you are aware that the European Union has imposed a requirement that mobile phone manufacturers need to provide now 5 years of software updates, which will make a huge difference. I think the same logic actually applies to the hardware in the shared infrastructure layers of the system. So network operators, they're replacing devices because they eclipse capacity, but because demand eclipses capacity. There's one reason, but they also have a need to replace, or they're driven to replace devices because the manufacturers cease to provide software updates. So the same applies there. So I think that's a big opportunity. It is, I think, the decision of what is the right rate of innovation and where will be the balance with increasing efficiency that we get from innovation versus the turnover. I think this is a more nuanced and detailed discussion that requires a really specific study of all system parts. That rate will vary depending on where you look. But I think we on a societal level that element of not replacing our mobile phones every 2 years, that has a big opportunity. And now with AR and VR, potentially there's the next market segment where we'll see the same kind of logic with only slightly modified new generations of devices incentivized through those business models to replace perfectly functioning devices.
Okay, thank you so much. So perhaps you can continue the discussion on the way for Le Diapason, where we can have lunch. We need just 5 minutes to go there, so we will be right on time. And then we will continue the session this afternoon with 3 presentations. The presentation of Daniel, Eric, and myself. Okay. Thanks a lot.